Bismillah ar-Rahman ar-Rahim. Welcome to chapter 7, Energy of a System. Energy of a System. If you remember the last announcement, we said 7.1 is cancelled. Well, however, it's a long section, talks a lot. However, we ask you just to understand one slide from 7.1 because it will help us when we talk about different systems and we solve different systems. So a system could be a single object or a particle, could be a collection of objects or particles, could be a region of space, not the whole space, just a region of space. For example, the interior of an automobile engine. And it may vary with time in size and shape. And we will see that when we calculate the work, that sometimes it will vary by size and shape. It's like an introduction to when we talk about a system and environments. So let's skip the salad and start with the beef. Let's talk about work. Let's talk about work. Work in physics is defined as force vector dot product, and then we have displacement. And when we say dot product, we will see now how to perform a dot product mathematically. So we define work as a dot product between two vectors, vector F, the force, and vector D, the displacement, or in our book he referred to it as delta R. So this is D. And when you go for in mathematics, what is a dot product? Well, it is F, the magnitude of the force, multiplied by the magnitude of the displacement, and then cosine theta, and theta is the angle between displacement. So this is displacement, and this is F, and this is theta. So it is the magnitude of the force, the magnitude of the displacement, and then we take the cosine of the angle between F and D. And the cosine has a sweet, let's say, a sweet meaning, because when we have a vector, that is vector A, and this is the x-axis, and this is theta, this is the y-axis. When we say the x component, this is the x component, and what is the x component equal? It's the magnitude of A cosine theta. So basically the meaning of the dot product is the component of the force in the same direction of the displacement, that is will give us work. So the y component will not do any work. The y component will not do any work in the x direction. So the only force that will do work in the x direction is the force in the x direction. For that we take a cosine. For that, we take a cosine. طيب, now let's see how we can perform a dot product and what are the rules of the dot product. Muhammad said, what if displacement was in their direction, in the y direction? If the displacement in the y direction, then the force in the x direction cannot do any work. Only the force in the y direction will do work. The force in the x direction will do no work. You take sine. Well, if you still consider, so this is x, this is y, and then Muhammad said that, okay, this is displacement and this is force, and we still call this theta. Yes, in this situation, so this is force. In this situation, it will be sine if that will do the work. But when you have this situation, we will consider this angle. We call it alpha, and then work is equal f d cosine alpha. Cosine alpha. And we know that, well, cosine alpha is equal sine theta. So to stick to one definition, we always consider the angle is between the force and the displacement, and we look for the angle that is adjacent to the displacement. So when the displacement in this direction, we'll look for alpha, not theta. We'll look for alpha, and then it becomes cosine alpha. We don't say it is sine theta. If you want to play with words, yes, it is sine theta, but when we define the angle, it is the angle adjacent to the displacement. طيب. So let's see the rules for the dot product. الحين, let me remind you that when we talked about vectors in chapter 2, I think, or chapter 3, I'm not sure. When we talk about the vectors, yeah, shukran Yusuf, chapter 3, we said it's when we have vectors, we have operators. We don't have a multiplication like 2 multiplied by 3 is equal 6. We don't have this multiplication in vectors. In vectors, either we have dot product or we have cross product. So now it is time to introduce for you a dot product. A dot product. And a dot product will result into a magnitude without a direction. So two vectors, if you dot product them, you end up with a quantity with no vector. In our case, you will end up with joule, and joule is not a vector. Joule is not a vector. So the first rule, A dot B is equal B dot A. Dot product, it will not make a difference if you do A dot B or B dot A. Also, if you have this situation, if you add the two vectors first and then multiply it by A, it's the same. If you multiply A by B, dot product, it's not multiplication. Be careful, multiplication for numbers. For vectors, we say it's A dot B plus A dot C, or we do B plus C and we dot product with A, it will be the same. When that's correct, it's when we have two vectors and we dot product them, the answer will be just a number, scalar, not a vector, and the magnitude of that scalar is the magnitude of A multiply the magnitude of B and then cosine theta. And theta is the angle between A and B. When we come to cross product, we will explain cross product. It's completely different. By the way, a cross product will give you a vector perpendicular to both vectors. That's a different story. So let us not to confuse ourselves. Now we are talking about dot product. طيب, suppose that A and B are perpendicular to each other, then right away their dot product will result into a 0. That's correct. Cosine 90 is 0. Now if A and B are parallel, A is parallel to B, and the angle between them is 0, then A dot B is nothing but AB, the magnitude of A multiplied by the magnitude of B. And if they are parallel but opposite in sign, yani the angle 180, it will be just a minus sign, the magnitude of A multiplied by the magnitude of B. To do a dot product, we need to understand this fact. In I square, or I multiply by I, will give me 1. J multiplied by J will give me 1. K multiplied by K will give me 1. And I, J, and K are unit vectors. Unit vectors. If you cross product the unit vectors, any two unit vectors, it will give you a 0 value. I dot J or I dot K or J dot K or whatever, it will just give me a 0. So basically, if we have two vectors, and we will have a numeric example soon, but if you have a vector A and a vector B, and we have 3 components for each vector, then A dot B will have just component A multiplied by in the I direction, it's the component AX multiplied by BX. Of course, if you want to fully do it, well, it's BX multiplied by AX, I square. I square is 1, so you end up with AX BX plus BXI multiplied by AYJ. And you have I and J, that's a 0. And you have BXI multiplied by AZK, and I by K is equal 0. So everything will disappear except for those 3 components. This is a number, and this is a number, and this is a number, so you end up with a number. No vector, just a number, a scalar. And in the case you have A dot A, it's just A square, AX square plus AY square plus AZ square. I think now we'll do a mathematical example just to clarify things. What's the difference between what? This slide and this slide? Yeah, what's the difference between the last 2 properties of A and B? This is parallel, this is anti-parallel. So this is A, and this is B in this situation. And in this situation, you could have A like this, and you can have B like this, or the reverse. So this is anti-parallel, this is parallel. ax square will be 1. This one? No, ax square, whatever component. But I square is 1. I square is 1. But ax square could be any value. For example, if the x component is 3, ax square will be 9. Let's do a mathematical example just to illustrate what we are talking about. Here we have vector A and vector B are in the xy plane. So there is no z component. There is no k component. And we want to do the dot product for both vectors. So practically we do 2 multiplied by minus 1, that is minus 2. That is minus 2. And we do 3 multiplied by 2, that's plus 6. So the result right away is 4. Why he is doing that? He is just to explaining for you how we do the multiplication. So first, 2i multiplied by minus I, it's minus I squared 2, so the answer is minus 2. You have I and j, the answer is 0. And you have j and I, the answer is 0. And you have j and j, the answer is 1. So we end up with minus 2 plus 6, and the answer is 4. It's the same rule, but any cross unit vectors, if you cross them, the answer is 0. So you can just skip it. You can just skip it when you cross the unit vectors. If you don't cross the unit vectors, then I multiplied by I is 1, j multiplied by j is 1, k multiplied by k is 1. If you cross the unit vectors, the answer is 0. So you can skip them. To add vectors to get the total force on x and y. I don't understand your question, Ahmed. If you can talk with the microphone or retype it. تفضل يا أحمد.
So my question is, why do we multiply vectors? Like we used to add them to get the total force and on the y and x axis. But why
that's correct. That is the total force. That's a vector. Now we are talking about work. Work by definition is a dot product between the force and the displacement, by definition. So we don't add vectors, we don't subtract vectors, we dot product vectors to get the work.
So this can be our velocity or
there is no velocity here. Yeah, there is no velocity. It's just work. The unit of A, the unit is in Newton, and B in this situation is meter. So Newton meter, which is Newton meter, which is a joule. Which is just a joule. We are talking about joule.
Okay.
طيب. What did you see here? It's as usual when I say it's a typical question that you find it in all physics books. Most likely he will give you 2 vectors. That's in general in mathematics. And if you are not doing a physics course in mathematics, he will give you 2 vectors and he will ask you to find the angle between them. So in order to find the angle between them, you need first to do a dot product, and then you find the length of each vector, and then you find the angle between them. However, in physics, we will just tell you that the first vector is force, the second vector is displacement, and we will ask you find the angle between the force and displacement. So basically, the second part is a typical question. Of course, work is a scalar quantity. So first of all, we calculate A dot B. It is 4 joule. If it is, if A is equal the force and B is equal displacement, then the answer A dot B will be 4 joule. طيب, this is the first part. How to find the angle? Well, we need to find the length of A, the length of B, and then after that we can find the angle. So the length of A is 2 square plus 3 square under square root of 13. Same thing for B. So now we know the value of AB and we know the dot product. So right away we can calculate the angle between them. You will see this in so many physics books talking about work. They have the same question. And even in mathematics, you will find it, but it's not force and displacement. You just give you A and B, two vectors. So here there is a mistake in the book. Here there is a minus sign. طبعا, all what we are talking about now, no, we assume that force is constant. Up to now, force is constant. Because if force is changing, we have a different way to solve our problem. But to make it easy, it's just a constant force. A particle moving in the XY plane undergoes, and he gave us the displacement. And he gave us the force, and calculate the work done by the force on that particle. So directly, it is just a dot product. He did it here in details. You don't need to do it in details if you are sure of yourself, because I and J will cancel. J and I will cancel. So if you are sure of yourself, you don't need to show that. You just give me the final answer. So it's 10 and 6, so it's 16 joule. It is 16 joule. Now let's talk about when the force is varying. So the force is not constant anymore. Well, as usually we do in calculus, we say for this very small rectangle, for a very small rectangle, the F dot D is just the area of this small rectangle. So if we divide the area into small rectangles and we add them all, it will give us the work. It will give us the work when force is not constant. So it's the summation of rectangles. So you know, integral is nothing but the area under the curve. The area under the curve. So we take the summation for the limit that those rectangles become very, very small until they reach 0. And this is nothing but the integral. So basically, when the force is a variable, work is nothing but the integral of x dx. Of not x, it is the force x in the x direction. So this is fx, that means this is the force in the x direction dx. So that is the work when the force is variable. When the force is variable, we do just integration. And we said that before. We said if you have x versus t and you take the derivative of that, you go for, you reach the velocity. And if you take the derivative of velocity with respect to time, you reach the acceleration. And the equivalent of derivative is the slope on the graph. And if you have the acceleration function and you want to go back to velocity, you integrate. And if you have the velocity function and you go back to the displacement, you integrate. And if you do what is integration on the graph, it is just finding the area. It is just finding the area. Yusuf said x is the distance. No, it's not the distance, it's the displacement. Distance is a scalar. Work, we do a dot product between two vectors. So force as a vector and displacement as a vector. It's not the distance anymore. طيب, let's summarize. Well, first, if you have a force in the x direction, variable force in the x direction, and we want to calculate the work in the x direction, so we use this formula. Now, and the summation, that means it's the net forces. The net forces, يعني the net force for several forces in general. You can have unlimited forces, but we take the net of those forces. طيب, what is now the situation? The force is in the x direction, but we want to calculate the work for that force in the x and in the y and in the z. In the x, the y, and the z. So we go for the general formula. And finally, if a deformable system, that means the system is not rigid. Yani if the system cannot be modeled as a particle, yani the system is not rigid enough for the applied force, like a softball, for example, well, in that situation, we divide this object into areas, different areas, and we do the integration separately for each force. We do the integration separately for each force acting on that particular part of that soft body, and then we add the total works. We add the total works. طيب. Now let's emphasize about what is the work. The work is nothing but the area under the curve. A force acting on a particle varies with x as shown. So this is the force. Constant from 1 to 4 meters displacement, and then it will vanish. It will vanish. It will go to 0 from 4 to 6 meters. As shown, calculate the work done by the force on the particle as it moves from x is equal 0 to x is equal 6. Well, it's just the area. It is just the area under the curve. So what's the area here for the rectangle? It's 20. 4 multiplied by 5, it's 20. And 4 to 6 multiplied by 5 divided by 2. So that is 5. And we add them, so it will give me 25 joule. It will give me 25 joule. So it is the area under the curve. And of course, if the force is varying more rapidly, we just take the integral, which is the area under the graph, the area under the function. طيب هلا we are going to take 3. We need to have an equation in that case. Yes, I will tell you, for example, that I will give you the force equation, and basically you integrate it in the x direction or in the y direction or in the z direction. Just normal integration. So here we are going to define work in regarding to 3 systems. The first system, we will see the relation between the work and the elastic energy of a spring. We will see the relation between work and the elastic energy of a spring. 2, we will see the relation between work and the change in kinetic energy. So the first part, work and the change in elastic energy of a spring. Second part, it's work and the change in kinetic energy. And the third part is work and change in potential energy. And by the way, those 3 types of forces, we call them mechanical energy. And those forces are conservative forces. And if you didn't do the lab yet, we have one of the experiments, conservation of mechanical energy. We do an experiment in 192 of conservation of mechanical energy. Well, those 3 types are conservative forces. We call it conservative forces. And we call it also mechanical energy. When you transfer energy from one type to another, energy is conserved. No energy is joule, and energy is a scalar. Force is a vector, and the unit of force is Newton. So they are completely two different things. One is a vector, one is a scalar. One unit is Newton, the other unit is joule. طيب, let's see mechanical energy. All 3 we can call it as mechanical energy: potential, kinetic, and elastic. Also we have rotational. Also it's a mechanical energy. In the book he didn't call them mechanical, but because we are going to do an experiment, mechanical energy, other books, those type of energy, those type of conservative energies, they call them mechanical energy. So you know that what you are going to cover in the lab. In the lab we have an experiment, a conservation of mechanical energy, and there we have rotational energy, we have potential energy, and we have kinetic energy. That energy will just transfer from one kind to another. طيب, so let's try to study the spring. So the first situation, equilibrium, it's at x is equal 0. When x is positive, that is x, so positive to the right and negative to the left. So when x is positive, a stretched spring, the spring force is directed to the left. And this is sometimes students will finish 191 and finish 192 and they have no idea about why Hooke's law have a minus sign. You know Hooke's law? You know Hooke's law? F is equal minus kx. That's Hooke's law. And also we have an experiment in the lab about Hooke's law. But some students sometimes are confused. Is it minus kx or plus kx? Well, if you are talking about the restoring force of the spring, you put a minus sign. And why is that? Because we just explained it. Displacement is positive. Where is the force of the spring? It is opposing. So we put a minus sign. However, if we are talking about the gravitational force or the human force that will force the spring to compress or to elongate, then it is F is equal kx. So let me just write it. F human مثلا or gravity, then it's equal kx. So this force, this is a restoring force of the spring. K is the spring constant, that's correct. شو يعني restoring force؟ يعني the spring has no force by itself. You force the spring to compress or to elongate, and as a result you have a restoring force, and that restoring force is negative. However, if you talk about your force, which is compressing the spring or elongating the spring, then we can write it. This is F human. It will be in the same direction of the displacement, either elongation to the right or compression to the left. That's the force of a human, for example, or the acting force. Restoring force, it's the opposite. So when x is 0, natural length of the spring force is 0. And when it is negative, the force is always opposing. Always opposing. So Hooke's law is F of the spring is equal minus kx. تفضل يا عادل.
So doctor, like, just to ensure, basically Hooke's law, the Fs is only about the spring itself. We're not talking about human force.
Of course, if you want to talk about human force or the acting force, if it is gravity or whatever, Hooke's law become F is equal kx.
It will be the opposite of
That's correct.
Hooke's law.
Well, it is both of them are Hooke's law, but depending on if it is the acting force or the restoring force. If it is the acting force, it's positive. If the restoring force, it's negative.
Okay, and another thing, that if the spring was compressed, the Hooke's law will have positive sign, right? Because x will be negative and that will cancel the other.
No. If it is compressed or
Yeah.
elongated depending on the type of the force. If you are talking about the acting force, it's always positive, always in the same direction of displacement. Always
Yeah.
in the same direction of displacement. So if you compress, x is negative and force is negative. So negative and negative become positive. When you elongate, x is positive and force is positive. Positive and positive is positive. Now, if you're talking about the restoring force, then when you compress the force, the restoring force is opposing to your compression. That's a negative sign. And when you elongate, the restoring force is pointing the other direction, so it's a negative. So
But
that's
Doctor, like if we compress the spring and the restoring force,
yeah,
like
here.
look at the
So
front.
okay, you are talking about this situation. Now x is negative,
Yeah.
the restoring force is positive. So positive and negative it's a
Yeah.
negative.
Because Hooke's law has negative k, and if the displacement was negative, we will have a restoring force which would be positive.
No.
Is that right?
Hooke's law k is always positive. In Hooke's law,
Okay.
k is always positive. But if you are talking about the spring, it will be a restoring force always opposing the x.
Okay, got it.
Okay. طيب. طبعا as you can see, if f of the spring is equal minus kx, that is a varying force. It's not a constant force. It's not a constant force. So based on x, you will determine the force. So if x is equal 1, for example, k is equal 10. When x is equal 1, you have 10 Newton. When x is equal 2, you have 20 Newton, etc., etc. So in the spring, force is not constant. Force is not constant. So we just apply our rule. It's not constant, so we take the integral. So we have the force dot dr, dr in general, but here we are talking about the x-axis only, so it's become just a dx. Dx because it's in the I component. And what is the force? We just said here is the force minus kx. So here is my force minus kx dx. And what is minus kx dx when you integrate? What is x when you integrate? What's the integration of x dx? It's x squared over 2. X squared? No. What's the integral of x dx is equal x squared over 2 from like whatever xi to x final. So here is xi and here is x final. So that means the integral of the force of the spring, it will give me half kx squared. Where the minus sign? Here the minus sign. It's minus x maximum to 0, so minus and minus become positive. Minus x maximum, and here you have a minus sign, so minus and minus will disappear. And we end up with half kx squared. And لاحظ انه x squared, so if x is positive, it will give you a positive value. If x is negative, it will give you a positive value. So work is here is positive. So if you compress the spring, you do a positive work. If you uncompress the spring, you do a positive work. If we are talking about work done by the spring, when it is compressed, it will do a positive work. When it is uncompressed, it will do a positive work. Does the equation give minus, whether it's minus x max or it's in the I direction? That's correct. It's in the I direction. It's in the I direction because we are studying the spring in the x-axis. And when you look at it, well, what's the area? This is the force, the straight line. And what is the area under that straight line? Well, it's half kx multiplied by x, that's kx squared. And because you have a triangle, so it's half the area, it's become half kx squared. And we integrate from x initial to x final of minus kx dx. So it will give me this result. And now pay attention that here we have k initial and here we have k final because we have a minus sign. We have a minus sign. Pay attention to this. So the work done by the spring, it's half kx initial square minus half kx final square, because we have a minus sign. We have a minus sign. In the previous example, already we have a minus x to start with, so the minus sign disappears. But here, because we don't know what is the minus x, we don't know the initial value of x, so it's x initial to x final. So usually this will give me whatever x final square. Let me just try it fully. So this usually will give me half kx square final minus half kx square initial, and we have a minus sign. We have a minus sign. So this minus sign and minus become positive, so you end up with half kx square I minus half kx final square. So be careful about that. And لاحظوا, please pay attention, this is the work done by the spring. The work done by the spring. When you look at the work done external, that means by the acting force. If it is a human force or gravitational force or whatever acting force, for the external force, it is the usual k final square minus k initial square. And why is that? Well, because now our applied force is positive, and then we end up with the usual amount. And you see right away that work external is equal minus the work of the spring. So if you do positive work on the spring will do negative work on you. So it's opposite in sign. That's correct. That's because always, again, let's repeat. If you are talking about the restoring force is always opposing the displacement. If you are talking about the acting force is always in the same direction of the displacement. So this is why we have a minus sign when we talk about the work done by the spring, and we have a positive sign when we talk about the work done by the acting force, which we refer to it as work external. Work external. Okay, so we end up with work external is nothing but the change in elastic energy. The change in elastic energy. So this is elastic energy اللي هي half kx square. Work of the spring and work of the acting force, applied force. Work external is always positive because the force in the same direction of the displacement. Work done by the spring is always negative to the work external because the force is always in the negative direction of the displacement. You do positive work on the spring will do negative work. Yeah, it is a scalar, and the negative here is to distinguish between the applied force or the restoring force. The minus sign here is to tell us if it is the restoring force or the applied force. We will come and see when we talk about the potential energy. You do positive work on gravitational force, and for example, to lift the object, you are doing a positive work. Gravity is doing a negative work. Why is negative? Because once you release the object will move because you stored your energy inside the potential energy, inside the gravitational force. So the minus sign, not because it's a vector, the minus sign is to tell you if it is the acting force or the restoring force. We'll have the same situation when we talk about potential energy. يعني one by one إن شاء الله يا محمد. XF is always 0 for X final. No. X final could be any value. Could be any value. You have a spring. There is no limitation, but you break your spring. X final has no limitation. Limitation of that you break your spring. That's it. But in principle, final displacement, initial displacement has no limit. So this is the first rule that we use to define work, external work. And we say external to differentiate it from the internal work or the system work. So the first rule, work external, is nothing but the change in elastic energy. The change in elastic energy. Now, let us talk about the relation between work and the change in kinetic energy. Change in kinetic energy. We start with f is not constant, so we do an integral of f dx. But what is f? It is ma. And what is a? It's dv over dt. But what is v? Well, v is dx over dt. So dx over dt. And we have dv over dx. So we can loosely, it's not a strictly mathematical thing to do, but loosely, we can just say, well, this can cancel with this, and we end what is dx over dt, it's a v, so we end up with mv dv. تفضل.
We said that that v is equal to dx dt.
صحيح.
But why did you make dv dx? Why did you put dv dx?
لاحظ, يعني this is mathematical, it's not physics, but we start dv over dt multiplied by dx, dx. If we add dx over dx, nothing will happen. Correct? Now let's rearrange it. So become dx over dt multiplied by dx multiplied by dv, and dx will go with dx. So we end up with dx over dt dv, and we return it back to its original value, so it becomes v dv. When you add dx over dx, it will not change anything, but it will just change your variable.
Okay, how about the dv is equal to dx over dt? Where did the
لا مش dv.
square?
dv is not equal to dx over dt. v is equal to dx over dt. dv is a variable.
Okay, so where did the dt go? It shouldn't be like dt square?
Why dt square, يا شيخ?
Because v is equal to dx over dt, and there was already dt done from the second equation to the third.
Yeah, that's يعني let me color it for you. Watch carefully. So we have dv over dt multiplied by dx. Yes? Now I multiply it by dx over dx. And then I have dx over dt dv dx over dx. So this will disappear with this. I end up with this. This is dx over dt, so that's a v and dv. So we end up with this integral mv dv. What's the integral? It's the same trick that we use. It's v squared over 2. So work external is half mv square final minus half mv square initial, and we call half mv square kinetic energy, and basically work external can be defined as the change in kinetic energy. So this is the second definition of work external. It's the change of kinetic energy. لاحظوا هون work external change in elastic energy, and here work external can be defined as change in kinetic energy. K final minus K initial. And this is work external. This is work external. Now, when work is done on a system, and the only change in the system is in the speed of its members, the net work done on the system equals, لاحظوا, on the system. مش الwork done from the system, it's on work done on the system. Done on the system equals the change in kinetic energy. I will call it work external. طيب, let's do this numerical example. A 6 kilogram block initially, then first of all 6 kilogram, that's the mass, he gave us the mass. Initially at rest, V naught is equal 0, is pulled to the right along frictionless, no friction, which is very, very simplified problem. Horizontal surface by constant horizontal force, and he gave us the magnitude of the force. Find the block's speed after it has moved through horizontal distance of 3 meters. الحين a lot of students will say, okay, we have the force, we have the mass, let's find the acceleration, ya Ustad, and we have the distance. So after we find the distance, we can find V final. I will tell you, yes, it will give the same exact result, but be careful. When I give you this kind of problem, I will write a small line that solve this problem using the energy concept. So if you solve this problem using kinematics, you will take 0. You get the point? If I don't say, yeah, you can solve it using kinematics, no problem. But if I ask you that solve this problem using the conservation of energy, and you solve it by kinematics, you will take 0. They will give the same result, but I want to test if you can solve it with conservation of energy. Clear? So work external is the change in kinetic energy. So it started from rest. So K initial was 0. K final, V final is the one that we are looking for. So V final is 2 work external divided by the mass. And what is the work? It's F, magnitude of F, multiplied by the magnitude of X, the displacement. And why is that? Because he already telling us that the direction of the force in the same direction of X. So no need to do cosine. So 2 multiplied by 12 Newton multiplied by 3 divided by 6 kilogram, it will give me the final speed. And this is one simple example of how you can calculate the speed and acceleration or whatever using the concept of conservation of energy. Conservation of energy. And there are some very interesting problems to use the concept of energy in order to find the speed or whatever. So it's a very fertilized area for a professor to give a question in this using the concept of conservation of energy. طيب الحين this is a typical problem, you will find it in most of physics books. A man wishes to load a refrigerator on a truck using a ram at an angle theta as shown in the figure. He claims that less work would be required to load the truck if the length L of the ram were increased so that the angle theta would be smaller. Is his claim valid? طبعا the answer is no. The answer is no. لأنه when we talk about conservative forces, by definition, a conservative force does not depend on the path. Conservative force does not depend on the path. يعني for example, this is the ground and this is a height of 10 meters. If I go directly from 0 to 10, I will have mgh, and if I go this way, the energy will be also mgh. It's the same. Does not depend on the path. Does not depend on the path. So here in the book, to convince you, he said, yes, the work done by the man and the work done by gravity. The man angle is 0, the gravity angle is 90, and he added cosine theta plus 90. Well, it is sine theta. So you end up with L sine theta, and L sine theta is nothing but mgh. So in terms of work, it will not make any difference. لأنه there is a restoring force. It's like the spring. When you lift an object against gravity, you do positive work, and gravity will do negative work by definition. And the negative sign, that means you are doing the work and gravity is storing the energy. This is why you put a minus sign. It's like the spring. You are compressing the spring, so you are doing positive work, and the spring is storing that energy, so we give it a minus sign. Minus because we are talking about the spring work. It's a minus. It's not, the spring cannot do work by itself unless you compress it. Gravitational force, if it is on the surface, it cannot do any work. You need to lift it. You do positive work, and the gravity will do negative work. And negative because you are storing energy.
Doctor, why did we take cosine theta plus 90 instead of sine theta?
لأنه he is adding work done by the man, work done by gravity. By the man, it's a 0 degree, and by gravity is 90 degree. The force of the man is in the direction of the motion. So this is the force of the man. So the force of the man is in the same direction of L. So the angle is 0. And the force of gravity is perpendicular. So that is mg. It's perpendicular. So the angle is 90. So cosine theta plus 90 degree, it will give me sine theta. Try it in your calculator.
It actually gives minus sine theta. That's why the minus cancels.
Yeah. So it will give the same work because work does not depend on the path. طيب, what will make difference? Well, look at it from this angle. What's the difference? What difference it will make when you use a ramp instead of lifting it directly vertical? Well, we took that before. We said this is mg. And what is the component of mg in this direction? That is mg sine theta. So that means the man force, at least, he need mg sine theta in the opposite direction. However, if he want to lift it up, he will need mg. He will need mg. When he use the ramp, he will use only mg sine theta. So the advantage of using a ramp is to reduce the force he is doing to lift the fridge. But he will do the same work. Increase the distance to minimize the force. And of course, the distance will depend on the angle. So basically, decrease the angle, you will end up doing less work, less force. Work is constant. Work is always constant. However, the smaller the angle, the smaller the force you need to push your fridge. That's the advantage. It will be easier to lift the object to the certain height. But in terms of energy, it is the same. In terms of force, it is much easier to lift your object. Yeah? I think like this, it will just make things very clear. The component of the gravity here is mg sine theta. And at least he need mg sine theta on the opposite direction to move with a constant speed, no acceleration. So in that case, mg sine theta is smaller than mg. And the smaller the angle, the smaller mg sine theta will be. So it will be easier. As long as you make the angle smaller, it will be easier to move things. طيب, إذن أخذنا العلاقة الأولى. We said the first part, we defined work as a change in kinetic energy. We defined work as change in elastic energy. وخلص علينا الوقت أصلا, صارت 12 و 15. So we stop here. إن شاء الله. We continue next time. Let me stop the recording.